Earth, our magnificent home in the vast universe, is the only known planet where life exists. Often called the blue planet, it glows with oceans, clouds, and life in every corner. From its molten core to its icy poles, Earth is a masterpiece of balance and mystery. It's a world where continents drift, seasons change, and life thrives in forms beyond imagination. Today, we'll uncover the most fascinating facts about this extraordinary planet. So, watch this video till the end and subscribe to the channel. Let's begin. Long before humans ever walked the surface, before oceans shimmered and skies turned blue, Earth was a chaotic, molten world forming from cosmic dust and gas left behind by the birth of the Sun. Scientists estimate that this process began about 4.54 billion years ago, a number uncovered through remarkable detective work. By studying the ages of ancient meteorites, fragments that formed at the same time as Earth, and using techniques like radiometric dating on the oldest rocks, scientists have pieced together the story of our planet's beginning. These methods rely on the steady decay of radioactive elements, like uranium turning into lead, allowing scientists to read time written in atoms themselves. In its earliest days, Earth was unrecognizable, a fiery globe bombarded by asteroids, its surface boiling with molten rock. Over millions of years, it cooled enough for solid crust to form, and eventually, water condensed to create vast oceans. Then, somewhere around 3.5 billion years ago, something extraordinary happened. Life appeared. Tiny microorganisms, likely thriving in deep-sea vents or shallow tidal pools, became the planet's first living inhabitants. These microscopic pioneers set in motion the long, intricate story of evolution, one that would one day lead to forests, animals, and humanity itself. And as Earth's surface began to solidify and stabilize, something powerful stirred beneath. Immense forces that would soon start shaping the continents themselves. Beneath our feet lies a world hidden from sight, a vast and complex structure that makes up the body of our planet. Though we only see the surface, Earth is made of four main layers: the crust, the mantle, the outer core, and the inner core, each one unique, yet deeply connected to the planet's overall behavior. The crust is Earth's outer skin, thin and fragile compared to the layers beneath it. It's where we live, build, and explore. But in reality, it's just a sliver, ranging from about 5 kilometers thick beneath the oceans to around 70 kilometers under mountain ranges. Below it lies the mantle, a massive layer of semi-solid rock that extends nearly 2,900 kilometers deep. The mantle isn't entirely solid. Its rocks can slowly flow, creating convection currents that drive the movement of Earth's crustal plates above. Deeper still lies the outer core, a swirling sea of molten iron and nickel. This layer, constantly churning due to Earth's rotation and internal heat, is the source of our planet's magnetic field, a powerful invisible shield that protects us from solar radiation. At the very center lies the inner core, a solid sphere composed mostly of iron. Despite being under unimaginable pressure, it remains solid, and its temperature is astonishing, reaching up to 5,500 degrees Celsius, roughly as hot as the surface of the Sun. This layered structure doesn't just define Earth's composition, it's the engine behind earthquakes, volcanic eruptions, and the slow drift of continents. And as these mighty forces push and pull from within, the surface above is constantly reshaped, a process known as plate tectonics, which tells the next great story of our planet's restless nature. The solid ground beneath us might seem still and unmoving, but in reality, Earth's surface is alive with motion. The planet's crust isn't one continuous shell. It's broken into enormous slabs called tectonic plates, which float on the semi-fluid mantle beneath them. These plates are in constant, slow motion, shifting a few centimeters each year, about the speed at which your fingernails grow. Yet, over millions of years, their steady movement reshapes the entire face of our world. Where plates meet, incredible geological events occur. At divergent boundaries, plates pull apart, allowing molten rock to rise and form new crust. This process creates mid-ocean ridges and volcanic islands. At convergent boundaries, plates collide, forcing one beneath the other in a process known as subduction. This immense pressure pushes up towering mountain ranges like the Himalayas and fuels volcanic activity along regions such as the Pacific Ring of Fire. At transform boundaries, plates slide past each other, creating friction that releases sudden bursts of energy, the cause of powerful earthquakes like those along California's San Andreas Fault. These slow, ceaseless movements are the sculptors of continents and oceans, the invisible artists shaping valleys, islands, and ranges that define our landscapes. Without plate tectonics, Earth would be geologically stagnant. No mountain peaks, no ocean trenches, no dynamic planet teeming with geological diversity. It's this restless motion that keeps our planet alive from within, continuously renewing its surface and influencing the habitats and climates above. And as these plates shift and collide, they also help shape something else that defines our planet's identity: the vast, glimmering oceans that earned Earth its most famous nickname, the Blue Planet. From space, Earth stands out like no other, a brilliant sphere draped in swirls of white clouds and endless shades of blue. This shimmering blue hue has earned our planet its famous nickname, the Blue Planet. More than 70% of Earth's surface is covered in water, a feature that makes it utterly unique among the worlds we've explored. Oceans stretch across vast distances, connecting continents and shaping our climate, weather, and even the rhythm of life itself. Yet, while water seems abundant, the truth is far more fragile. Of all the water on Earth, about 97% lies in salty oceans, undrinkable without costly desalination. The remaining 3% is freshwater, but most of that is locked away in glaciers, polar ice caps, or deep underground aquifers. In reality, less than 1% of Earth's total water is easily accessible, found in rivers, lakes, and the shallow groundwater we rely on for drinking, farming, and daily life. This delicate balance makes water one of our most precious resources. Oceans regulate temperature, absorb carbon dioxide, and produce more than half of the oxygen we breathe through microscopic plankton. They also act as the planet's great highways, influencing weather systems and supporting a vast web of life, from the smallest coral polyp to the largest blue whale. The tides rise and fall, currents circulate heat around the globe, and rainfall nourishes forests and fields, all thanks to the interconnected dance of Earth's water systems. But it's not just water that sustains life. The invisible layer surrounding our world, our atmosphere, plays an equally vital role in protecting and nurturing everything that breathes. The blanket of air that surrounds Earth is far more than just the sky we see. It's a dynamic, multi-layered shield that makes life possible. Without it, our world would be a barren rock, scorched by the sun by day and frozen solid by night. This remarkable envelope of gases, our atmosphere, not only gives us air to breathe, but also acts as Earth's guardian, moderating temperature, absorbing radiation, and burning up meteors before they can reach the ground. It's delicate and invisible, yet it defines the boundary between life and lifelessness. Earth's atmosphere is composed mostly of nitrogen, about 78%, and oxygen, around 21%, with traces of argon, carbon dioxide, water vapor, and other gases that together create a perfect chemical balance. This mix didn't always exist. Billions of years ago, volcanic eruptions release toxic gases like methane and ammonia into the early atmosphere. Over time, through the work of microscopic organisms and countless geological processes, it transformed into the breathable air we depend on today. But the atmosphere isn't uniform. It's divided into distinct layers, each with its own unique properties and purpose. Closest to the surface is the troposphere, the layer where we live, breathe, and experience weather. It extends up to about 8 to 15 kilometers above the surface and contains around 75% of the atmosphere's mass. Here, clouds form, winds blow, and storms take shape, all driven by the uneven heating of Earth's surface by the sun. The temperature in the troposphere drops steadily as altitude increases, which is why mountaintops are colder than valleys. Above that lies the stratosphere, extending from around 15 to 50 kilometers above the surface. This is the layer where the ozone layer resides, one of the most crucial shields protecting life on Earth. The ozone layer absorbs the majority of the sun's harmful ultraviolet UV radiation, preventing it from reaching the surface where it could damage DNA and disrupt ecosystems. Interestingly, unlike the troposphere, the temperature in the stratosphere increases with altitude because ozone absorbs energy from sunlight, warming the surrounding air. Next comes the mesosphere, stretching up to about 85 kilometers high. It's here that meteors, small fragments of rock and metal from space, burn up as they enter the atmosphere, creating the beautiful streaks of light we call shooting stars. Without this layer, countless space rocks would strike Earth's surface daily. Above the mesosphere is the thermosphere, an enormous region that extends up to around 600 kilometers. Temperatures here can soar to over 2,000 degrees Celsius, 3,600 degrees Fahrenheit, due to the absorption of high-energy radiation from the sun, though the air is so thin that you wouldn't actually feel the heat. The auroras, those breathtaking displays of green, red, and purple light near the poles, occur in this layer as charged particles from the solar wind collide with atmospheric gases. Beyond that lies the exosphere, the outermost edge of Earth's atmosphere, gradually fading into the vacuum of space. It's incredibly thin, with particles so sparse they can travel hundreds of kilometers without colliding. This is where satellites orbit, delicately balanced between Earth's gravity and the pull of space beyond. The atmosphere does far more than just separate us from space. It's a living, breathing system in constant motion. It distributes heat through wind patterns and ocean interactions, cycles moisture through evaporation and rain, and even carries nutrients and dust across continents. It's the reason we have blue skies during the day, as sunlight scatters off air molecules, and stunning sunsets when the atmosphere filters light into warm hues. But perhaps its most vital role is as Earth's protector. It blocks dangerous radiation, deflects solar wind, and burns up small asteroids that would otherwise impact the surface. It moderates temperature extremes, ensuring that our planet doesn't freeze solid at night or boil during the day. In short, Earth's atmosphere is a masterpiece of balance, thick enough to sustain life, yet thin enough to let light and warmth through. However, this perfect balance exists only because Earth sits in just the right place in the cosmos. Our distance from the Sun, not too close and not too far, is the cosmic sweet spot that makes water, weather, and life itself possible. When it comes to life in the universe, location is everything. Earth's place in the solar system is nothing short of extraordinary, a delicate positioning in what astronomers call the Goldilocks zone. Just like the story of Goldilocks and the three bears, this zone isn't too hot and isn't too cold. It's just right. In this thin band of space around the Sun, conditions allow liquid water to exist on a planet's surface. And as far as we know, liquid water is the key ingredient for life. Earth orbits the Sun at an average distance of about 93 million miles, 150 million kilometers. This distance gives us a surface temperature range that allows water to exist in all three states: solid, liquid, and gas. If Earth were just a little closer to the Sun, our oceans would boil away, creating a runaway greenhouse effect like that of Venus, where surface temperatures reach nearly 475 degrees Celsius, 900 degrees Fahrenheit, hot enough to melt lead. If we were slightly farther, water would freeze solid, and our planet might resemble Mars, a world of cold deserts and frozen carbon dioxide. But here, in this perfect cosmic middle ground, Earth enjoys the ideal conditions for rivers to flow, clouds to form, and ecosystems to flourish. The Goldilocks zone isn't just about distance, it's also about balance. Earth's atmosphere plays a crucial role in regulating temperature. Greenhouse gases like carbon dioxide, methane, and water vapor trap some of the sun's heat, keeping the planet warm enough to sustain life. Without this natural greenhouse effect, our world would be a frozen wasteland with average temperatures around -18 degrees Celsius, 0 degrees Fahrenheit. Yet, with too many of these gases, Earth would overheat, showing how delicate this equilibrium truly is. Earth's perfect position also affects the amount of solar energy that reaches different parts of the planet. This variation, combined with the planet's tilt and rotation, drives the climate patterns and weather systems that make our world so diverse. From tropical rainforests to polar ice caps, every environment owes its existence to this finely tuned balance between sunlight and distance. It's also worth noting how rare this position may be. Out of billions of planets in our galaxy, only a small fraction are thought to lie within their star's habitable zone, and even fewer possess the right atmosphere, magnetic protection, and geological activity to maintain liquid water over billions of years. Earth has held this position for most of its history, despite gradual changes in the Sun's brightness and the planet's own orbital variations. That stability is one of the reasons life has been able to evolve and persist for such an astonishing span of time. This sweet spot in space doesn't just provide warmth and water, it also shields us from the extremes that could have snuffed out life before it began. The interplay between sunlight, gravity, and atmosphere keeps the planet's systems in harmony, ensuring that life can adapt, thrive, and continue. The Goldilocks zone, in many ways, is the cosmic cradle of life, and Earth's residence within it is one of the most remarkable coincidences in all of creation. But even this ideal distance wouldn't be enough if not for one more invisible protector, an unseen force generated deep within our planet. As we move from the gentle warmth of the sun to the fiery heart of Earth itself, we find another essential guardian of life, the magnetic field, an unseen shield that defends our world from deadly solar winds and cosmic radiation. Deep within Earth's interior, far beneath the crust and mantle, lies a realm of molten metal in perpetual motion, a churning ocean of liquid iron and nickel that serves as the beating heart of our planet. This restless movement, combined with Earth's rotation, gives rise to one of the most crucial and fascinating phenomena in the natural world, the magnetic field. It's invisible to the eye, yet it wraps around our planet like an invisible force field, shielding every living thing from cosmic harm. The source of this magnetic field lies in the outer core, a layer of molten metal roughly 2,200 kilometers thick, surrounding the solid inner core. As this molten iron moves and circulates, it generates electric currents. These currents, in turn, produce magnetic forces, a process known as the geodynamo. The geodynamo works much like a massive, self-sustaining electrical generator, powered by the heat escaping from the core and the planet's slow, steady spin. The result is an immense magnetic bubble that extends far beyond the atmosphere into space, forming what scientists call the magnetosphere. The magnetosphere plays a vital defensive role in protecting Earth from the solar wind. A constant stream of charged particles ejected from the Sun at speeds exceeding 1,000,000 miles per hour. Without the magnetic field, these particles would strip away our atmosphere over time, leaving the planet barren, just as solar winds did to Mars billions of years ago. Instead, Earth's magnetic field deflects most of this radiation, channeling it safely around the planet. Some particles do get trapped in regions known as the Van Allen radiation belts, circling high above the surface. But for the most part, life on Earth remains shielded from the Sun's fury. When the solar wind collides with Earth's magnetic field, it creates spectacular natural light shows near the poles. The aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere. These shimmering curtains of green, purple and red light dance across the night sky, the visible evidence of invisible battles between solar particles and Earth's magnetic shield. Each display is a cosmic reminder of the power and elegance of our planet's natural defenses. What's truly remarkable is that the magnetic field isn't fixed. It moves, fluctuates, and even reverses over geological timescales. The magnetic poles, where the field lines converge, drift over time, and roughly every few 100,000 years, they switch places entirely in what's known as a geomagnetic reversal. During these reversals, the strength of the field weakens temporarily before rebuilding itself, though scientists believe Earth's atmosphere and magnetosphere together still provide sufficient protection even during these transitions. The field also plays a critical role in navigation and animal behavior. Birds, sea turtles, and even some bacteria possess the ability to sense Earth's magnetic field, using it as a natural compass for migration and orientation. Humans, too, have long depended on this invisible force. From the earliest compasses guiding sailors across oceans to modern navigation systems still influenced by magnetic variation. Without this protective cocoon, life as we know it might never have flourished. Our atmosphere could have been stripped away, leaving a lifeless, desolate surface vulnerable to radiation. The magnetic field ensures not only our physical protection, but also our planet's stability and endurance. Yet, while the magnetic field defends us from the Sun's wrath, the rhythm of life on Earth is shaped by another force, one that gives us the cycle of day and night, the changing of seasons, and the passage of time itself. As our planet spins and tilts in the cosmic dance, it creates the daily and seasonal patterns that define our very existence. Every second of every day, even as we stand still, we are in motion, carried around the axis of our planet at remarkable speed. This continuous spin, unseen yet deeply felt, defines the rhythm of life on Earth. The planet's rotation and its subtle axial tilt are two of the most fundamental forces shaping our world, orchestrating the cycle of day and night, the pattern of seasons, and the gentle balance between light and darkness that sustains every living thing. Earth completes one full rotation on its axis, roughly every 24 hours. This invisible line, called the axis, runs from the North Pole to the South Pole, around which the planet spins like a top. Because of this motion, the Sun appears to rise in the east and set in the west, though in reality, it is Earth that is turning toward and away from the Sun. The speed of this rotation is astonishing. At the equator, the surface moves at about 1,670 kilometers per hour, 1,037 miles per hour. Yet we don't feel it, because everything, including the atmosphere, moves with us in perfect harmony. This daily rotation is what divides time into the cycle of day and night, providing the alternating periods of light and rest that govern life's rhythms. Plants open their leaves to the morning light, animals awaken to hunt or forage, and humans have built entire civilizations around the rising and setting of the sun. Beyond this natural clock, the rotation also affects the planet's shape and behavior in fascinating ways. Due to the centrifugal force of spinning, Earth isn't a perfect sphere, but an oblate spheroid, slightly flattened at the poles and bulging at the equator. This subtle distortion influences gravity and even ocean currents, tying Earth's physical form to its motion in space. But the rotation alone doesn't explain the diversity of climates and the precession of the seasons. For that, we must look to the planet's tilt. Earth's axis isn't perfectly upright. It's tilted at about 23.5 degrees relative to the plane of its orbit around the Sun. This tilt is one of the most critical factors in shaping the environment of our planet, because it determines how sunlight is distributed across the surface throughout the year. As Earth orbits the Sun over the course of 365.25 days, different parts of the planet receive varying amounts of solar energy. When the northern hemisphere is tilted toward the Sun, it experiences summer. Days grow longer, sunlight strikes more directly, and temperatures rise. At the same time, the southern hemisphere tilts away, experiencing winter, with shorter days and weaker sunlight. 6 months later, the situation reverses, bringing warmth to the south and cold to the north. The equinoxes, occurring around March 21st and September 23rd, mark the moments when neither hemisphere is tilted toward or away from the Sun, creating nearly equal day and night across the globe. This gentle wobble in orientation, steady yet profound, is the reason why we have such rich variety in climate and life. Without it, there would be no seasons at all. The equatorial regions would be perpetually hot, while the poles would remain locked in endless cold. But thanks to the tilt, the sunlight's path changes through the year, allowing plants to bloom, migrate, and rest in sync with the turning of the Earth. It's a natural rhythm that has guided evolution for billions of years and continues to influence everything from weather patterns to human agriculture. Interestingly, Earth's tilt isn't entirely fixed. Over long periods of time, it oscillates slightly, shifting between about 22 degrees and 24.5 degrees in a slow cycle lasting roughly 41,000 years. These variations, along with changes in Earth's orbit and the direction of its axis, a process called precession, contribute to long-term climate cycles known as Milankovitch cycles. These cycles are believed to play a significant role in the advance and retreat of ice ages, demonstrating how even slight changes in Earth's tilt can have enormous consequences for the planet's environment and life. The tilt also gives rise to one of the most awe-inspiring natural phenomena, the polar day and polar night. Near the Arctic and Antarctic circles, the sun doesn't rise or set for months at a time. During summer, the sun circles the horizon endlessly, bathing the landscape in continuous light, a period known as the midnight sun. In winter, it never rises at all, leaving the region in long twilight or complete darkness for weeks or months. These extremes test the endurance of life, yet countless species, from Arctic foxes to penguins, have evolved to thrive in them, living proof of nature's incredible adaptability to Earth's celestial dance. Even beyond life and light, Earth's rotation and tilt influence weather systems and ocean currents. The planet's spin gives rise to the Coriolis effect, a force that causes moving air and water to curve, shaping global wind patterns and the rotation of hurricanes and ocean gyres. Without this effect, weather would be drastically different, and the complex interplay between atmosphere and ocean, the heartbeat of our climate, would not exist as we know it. What's more, this rotation has been slowing down very gradually over time. Billions of years ago, Earth's day lasted only about 6 hours. The reason for the slowdown lies in the gravitational tug of our moon, which creates ocean tides that, through friction, gradually transfer rotational energy away from Earth. As a result, our days lengthen by roughly 1.7 milliseconds per century, an almost imperceptible change, yet one that will, over immense timescales, alter the rhythm of our planet. The combination of rotation and tilt is what gives Earth its dynamic and livable nature, a perfectly timed ballet between light and shadow, warmth and cold, motion and balance. It is a cosmic metronome that keeps the heartbeat of our world steady and predictable, enabling life to adapt to patterns that repeat endlessly yet never grow old. And while these movements shape our experience of time and climate, they also affect something deeper, the very shape and pull of the planet itself. Beneath the spinning surface lies another subtle secret. Earth is not perfectly round, and gravity's gentle variations across its surface remind us that even our planet's form is molded by motion. Though we often picture Earth as a perfect blue sphere floating serenely in space, the truth is more nuanced. Our planet is beautifully, subtly imperfect. Its shape tells a deeper story of motion, mass, and the invisible hand of gravity sculpting it over billions of years. Rather than a flawless ball, Earth is an oblate spheroid, slightly flattened at the poles and bulging gently at the equator. This seemingly small detail has vast implications for everything from how we measure sea level to how satellites orbit above. The reason for this imperfection lies in Earth's rotation. As the planet spins, the outward force, known as centrifugal force, causes the equatorial region to bulge outward, while the poles are pulled slightly inward. The result? A difference of about 43 kilometers, 27 miles, between Earth's polar and equatorial diameters. If you could shrink the Earth down to the size of a basketball, it would still look perfectly round to the naked eye, but in reality, it's a little squished at the top and bottom. This shape perfectly balances the competing forces of gravity and motion, allowing our planet to remain stable over immense periods of time. Gravity itself, though constant in principle, doesn't pull with equal strength everywhere on Earth. The acceleration due to gravity, what we usually call g, averages about 9.8 meters per second squared, but this value fluctuates slightly depending on where you are. Near the equator, gravity is a bit weaker because the bulge places you farther from Earth's center of mass, and because the centrifugal effect from rotation slightly counteracts gravity's pull. At the poles, however, you're closer to the center, and the rotation's influence is minimal, so gravity is stronger. This means that if you weighed 100 kilograms at the North Pole, you'd weigh about 99.5 kilograms at the equator, a subtle but measurable difference caused entirely by our planet's shape and spin. These variations aren't just due to rotation, they also reflect differences in Earth's internal structure and surface features. Mountain ranges, ocean trenches, and even the density of rock beneath the crust can alter local gravity. Areas with dense rock, like mountain roots or continental shields, exert a slightly stronger gravitational pull, while regions above lighter or molten material, such as volcanic zones, experience slightly weaker gravity. To map these minute fluctuations, scientists use satellites like the GRACE mission, Gravity Recovery and Climate Experiment, which measures tiny changes in Earth's gravitational field with extraordinary precision. These data reveal how mass moves around the planet, from melting ice sheets and shifting water to the slow flow of magma deep underground. This knowledge isn't just theoretical. Gravity's variations affect everything from sea level measurements to GPS accuracy. The concept of mean sea level, for instance, isn't actually flat. It rises and falls in accordance with local gravitational strength. In places where gravity is stronger, water is pulled slightly higher, creating a bulge in the ocean's surface. Conversely, in areas of weaker gravity, the sea surface dips slightly. So, the level oceans we imagine are actually undulating ever so gently under the influence of gravity's subtle dance. Even satellite orbits depend on these gravitational differences. When satellites circle Earth, they don't travel in perfect ellipses, but constantly adjust to the planet's irregular pull. This slight wobbling helps scientists refine models of Earth's shape, what's called the geoid, a precise three-dimensional representation of how gravity defines our planet's form. The geoid isn't smooth. It's full of gentle dips and rises that mirror the hidden topography of Earth's mass distribution. Our planet's gravity also plays a central role in holding everything, including the atmosphere and oceans, in place. Without it, Earth would be incapable of sustaining the delicate systems that make it habitable. Gravity keeps the air we breathe close to the surface, ensuring that oxygen, nitrogen, and water vapor don't drift into space. It governs the rise and fall of tides, the fall of rain, the growth of plants, and even the flow of rivers. It is, in essence, the force that unites every particle of our planet into one coherent whole. But what's even more remarkable is how Earth's gravity interacts with the Moon, our celestial companion. The gravitational pull between these two bodies creates ocean tides, stabilizes the planet's tilt, and influences life in subtle yet profound ways. The Moon, though small compared to Earth, exerts enough power to tug at our oceans and even at the crust itself. It is not just a distant light in the night sky. It is a vital partner in maintaining the stability that allows Earth to remain a haven for life. As we turn our gaze from the gentle curvature of Earth to the luminous face of our Moon, we uncover another chapter of the planet's story, one of gravitational harmony, cosmic partnership, and eternal influence. The Moon does far more than simply light the night. It has shaped Earth's history, its tides, and even the rhythm of life itself. Hanging in the night sky like a silent sentinel, Earth's Moon has watched over our planet for more than 4.5 billion years. It has guided explorers, inspired poets, and governed the natural rhythms of life itself. But beyond its serene glow, the Moon plays a far deeper role, one so essential that without it, Earth might be a vastly different, perhaps even uninhabitable world. Far from being a mere decorative companion, the Moon is one of the most influential forces shaping our planet's stability, oceans, and even the cycles that define the very heartbeat of life. To begin with, the Moon is an anomaly in our solar system. For a planet of Earth's size, having a moon so large is extremely rare. Our Moon is about 1/4 the diameter of Earth, making it the 5th largest moon in the solar system and the largest relative to its parent planet. Most moons are tiny compared to the worlds they orbit. Consider Jupiter, with dozens of small satellites, or Mars, whose 2 moons, Phobos and Deimos, are little more than captured asteroids. By contrast, Earth's Moon is massive enough that the 2 bodies actually orbit a shared center of gravity, a point located about 1,600 kilometers beneath Earth's surface. In a cosmic sense, Earth and the Moon are a true binary system, dancing around each other through the void. Scientists believe the Moon was born from violence. The most widely accepted theory, the giant impact hypothesis, suggests that around 4.5 billion years ago, a Mars-sized body named Theia collided with the early Earth. The force of this impact was catastrophic, ejecting vast amounts of molten material into orbit. Over time, this debris coalesced under gravity's pull, forming the glowing sphere we now see in our skies. That cataclysmic event reshaped both worlds. Earth gained a stabilizing companion, and the Moon became permanently locked in its orbit, its face forever turned toward us. One of the Moon's most vital contributions to our planet is its ability to stabilize Earth's axial tilt. As we explored earlier, Earth is tilted at about 23.5 degrees, and this tilt is what gives us our changing seasons. But without the Moon, that angle could fluctuate wildly due to gravitational influences from other planets, particularly Jupiter. Computer models suggest that without the Moon's steadying presence, Earth's tilt could vary by as much as 60 degrees over geological timescales. Such instability would lead to extreme and chaotic climate swings, ice ages, and scorching heat waves alternating unpredictably, making long-term life far more difficult to sustain. The Moon acts as a cosmic anchor, keeping Earth's rotation and tilt stable enough to maintain a relatively mild and consistent climate over billions of years. But perhaps the most immediate and visible influence of the Moon lies in the tides. Every day, the gravitational pull between the Earth and Moon causes the planet's oceans to bulge slightly, creating high and low tides that sweep across coastlines. The Moon's gravity pulls the ocean water on the side of Earth facing it outward, forming a bulge, the high tide. At the same time, another high tide forms on the opposite side due to the inertia of the water as the planet spins. Between these bulges are regions of lower water level or low tide. This constant rise and fall of the seas might seem simple, but it's one of the most powerful forces shaping Earth's environment. Tides regulate countless natural systems. They influence coastal ecosystems, redistribute nutrients, shape shorelines, and even help mix the ocean's waters, driving biological productivity. Many marine species, from crabs to coral, have evolved to depend on tidal rhythms. The Moon's pull quite literally governs the clock of coastal life. Long before humans tracked time with calendars or clocks, ancient organisms synchronized their lives to the lunar cycle, a rhythm that continues even now. This gravitational connection also affects Earth itself. The Moon's pull doesn't just move water, it flexes the solid crust ever so slightly, causing tidal forces that generate friction within the planet. Over millions of years, this friction has gradually slowed Earth's rotation. When the Moon first formed, a day on Earth may have lasted only about 6 hours. As tidal friction sapped the planet's rotational energy, the length of a day increased. At the same time, the Moon slowly drifted farther away, about 3.8 centimeters, 1.5 inches per year, as the system transferred angular momentum between the two bodies. This process continues even now, subtly reshaping the relationship between Earth and its companion. The Moon's influence reaches far beyond tides and rotation. Its phases, waxing, waning, full, and new, have guided humans for millennia, marking the passage of time long before modern calendars existed. Many ancient cultures built their entire calendars on the lunar month, which lasts about 29.5 days. These cycles also influence biological behavior. Many animals exhibit circulunar rhythms, biological cycles that sync with the phases of the Moon. For instance, certain species of coral release their eggs and sperm in mass spawning events precisely timed to the full moon. Even human sleep and mood patterns, though subtle, have been shown in some studies to correlate with the lunar cycle. There's also an emotional and cultural dimension to the Moon's presence. It has shaped mythology and art across civilizations, a constant, luminous companion linking every human generation. From the ancient Sumerians and Egyptians to the Mayans and Chinese, nearly every culture has woven stories about the Moon's origin and power. It has been a symbol of femininity, rebirth, time, and mystery, its waxing and waning mirroring the cycles of nature and life itself. Even in modern times, the Moon remains a powerful symbol of exploration and wonder, humanity's first step beyond our home planet. Scientifically, the Moon also plays a crucial role in reflecting sunlight to Earth. The albedo, or reflectivity, of the Moon brightens our night skies, providing natural illumination that once guided nocturnal animals and early humans before artificial light existed. This faint light has shaped nocturnal behavior and predator-prey dynamics for millions of years. Predators often use moonlight to hunt, while prey species adjust their activity to avoid being seen. In this way, even the moon's reflection has shaped evolutionary behavior. Its influence reaches into the planet's very mechanics as well. The gravitational tug between the Earth and Moon not only generates tides, but also creates tidal locking, the phenomenon that causes one side of the Moon to always face Earth. Because of this, we never see its far side from the surface. It remained a mystery until the space age revealed it to us through spacecraft imagery. This locked relationship adds to the gravitational stability of the system, keeping the Moon's orbit synchronized and Earth's spin predictable. If the Moon were gone, if it somehow drifted away or had never formed, the effects on Earth would be profound. Days would shorten as the planet's rotation sped up. The tilt of the axis would become unstable, and tides would diminish dramatically. Coastal ecosystems that depend on tidal rhythms would collapse. Weather patterns might become more erratic, and life's evolutionary path could have taken an entirely different course. Some scientists even speculate that the presence of such a large, stabilizing moon may have been a crucial factor in the emergence of complex life on Earth. So, the moon is not just a silent observer in the night sky. It is a dynamic, life-shaping partner in Earth's cosmic story. It stabilizes our tilt, moderates our climate, sets the rhythm of the seas, and influences life in countless subtle ways. It is both a scientific marvel and a timeless muse, linking the physical and the poetic aspects of existence. And as we look beyond the moon's silver glow back toward our planet, we see the result of billions of years of evolution and adaptation, a living world teeming with diversity. From the ocean's depths to the mountain peaks, life has filled every niche, adapting to every challenge. The next chapter in Earth's story reveals just how extraordinary that diversity truly is. The tale of life in all its infinite forms. Life on Earth is an intricate masterpiece, a living mosaic of forms, colors, and behaviors that has unfolded over billions of years. From the smallest microbe clinging to the walls of deep-sea vents to the majestic blue whale gliding through the open ocean, our planet is bursting with diversity. It is estimated that over 8.7 million species of plants, animals, fungi, and microorganisms share this world with us, though some scientists believe the true number could be closer to 100 million when including the yet undiscovered microbial life hidden in soils, ice caps, and ocean depths. Earth, unlike any other known world, is a canvas painted in the hues of evolution, where every living thing, no matter how small, plays a part in maintaining the balance of the planet's vast and delicate ecosystems. The roots of this diversity stretch deep into time. Life began humbly, around 3.5 billion years ago, with single-celled organisms, microscopic pioneers that learned to harness the energy of the sun and the chemistry of minerals. Over eons, these simple forms evolved into complex multicellular organisms, branching into countless lineages that conquered every corner of the globe. From the first bacteria that thrived in boiling seas to the early plants that greened the continents, evolution sculpted life through the twin forces of adaptation and natural selection, guided by the conditions of an ever-changing Earth. Today, life flourishes in environments so diverse and extreme that they seem impossible at first glance. Beneath crushing ocean pressures, entire ecosystems exist without sunlight, surviving instead on the chemical energy from Earth's inner heat. Around hydrothermal vents, deep in the darkness of the abyss, strange creatures like giant tube worms, ghostly crabs, and bioluminescent fish thrive in scalding, mineral-rich waters. In contrast, at the other extreme, in the frozen deserts of Antarctica, microscopic algae bloom beneath layers of ice, and tiny rotifers survive being frozen solid for years, only to awaken when thawed. On land, life's adaptability is equally astonishing. From the lush rainforests of the Amazon, home to more species of plants and animals than any other place on Earth, to the scorching dunes of the Sahara, where hardy reptiles and insects endure temperatures that would kill most creatures, life persists in endless variety. High on Mount Everest, where oxygen is thin and cold winds howl, a few hardy spiders, mosses, and microorganisms manage to survive. In the driest deserts, bacteria lie dormant in the soil, waiting years for a single drop of rain to awaken them. Even within Earth's crust, kilometers below the surface, scientists have discovered vast microbial communities living in total darkness, feeding on hydrogen, methane, and minerals. It is now clear that life is not fragile. It is resilient, persistent, and astonishingly creative. Among the grand tapestry of species, humans are but one thread. Remarkable, yes, but deeply interconnected with the rest. Every breath we take depends on microscopic phytoplankton in the oceans that produce more than half the planet's oxygen. Forests recycle carbon dioxide, insects pollinate crops, fungi decompose waste, and bacteria fix nitrogen in the soil, allowing plants to grow. Each species, no matter how insignificant it may seem, contributes to the web of life in ways we are only beginning to understand. Destroy one thread and others begin to unravel. A reminder that our survival is inseparable from the health of the ecosystems around us. This interdependence is what makes Earth's biosphere so special. It is a self-sustaining, self-regulating system, an intricate balance between producers, consumers, and decomposers, cycling energy and matter in an endless loop. The sun's energy flows through plants via photosynthesis into animals that feed on them and back into the soil through decay. This web of energy connects every living thing, from the smallest bacterium to the largest predator. Consider the oceans, which harbour around 90% of Earth's biomass. Within them lies an entire universe of life. Coral reefs, often called the rainforests of the sea, support a quarter of all marine species despite covering less than 1% of the ocean floor. Kelp forests sway along temperate coasts, providing shelter for fish, sea urchins, and seals. In the open ocean, plankton drift like cosmic dust in water, feeding the food chain that sustains whales, sharks, and seabirds. Even in the deepest trenches, where pressure is 1,000 times that at sea level, strange creatures glow with bioluminescence, creating eerie constellations in the abyss. On land, the variety is no less breathtaking. The tropical rainforests of South America, Africa, and Southeast Asia teem with life in every layer, from the canopy to the forest floor. A single tree in the Amazon can host more than 400 species of insects, each fulfilling a unique role. Grasslands support immense herds of grazing animals and the predators that hunt them, while wetlands serve as nurseries for fish and filters for fresh water. Even urban areas, which seem dominated by human structures, have become new ecosystems where adaptable species, pigeons, raccoons, foxes, and even coyotes, thrive alongside us. And yet, for all we've discovered, the majority of Earth's species remain a mystery. Scientists estimate that over 80% of the planet's biodiversity has not yet been identified. Every year, thousands of new species are discovered. Tiny frogs in the Amazon, glowing fungi in caves, deep-sea creatures with transparent bodies, and bacteria with potential to revolutionize medicine. Each discovery expands our understanding of life's ingenuity and reminds us that our planet is still a frontier of wonder. Life's diversity also reflects a profound truth. Adaptability is the essence of survival. Over millions of years, life has weathered 5 mass extinction events, from the asteroid impact that wiped out the dinosaurs to volcanic eruptions and ice ages that reshaped the planet. Yet each time, life rebounded, different but alive. It evolves, reshapes, and fills every niche left vacant. This relentless creativity of evolution has made Earth's biosphere more complex and interconnected with every passing era. But this incredible diversity does more than decorate our planet. It sustains it. Biodiversity regulates the climate, purifies air and water, controls disease, and maintains soil fertility. Every living organism contributes to the planetary balance. A silent cooperation forged through eons of coexistence. The more diverse life is, the more resilient Earth becomes to change. When diversity declines, ecosystems weaken, and the stability of the biosphere itself comes under threat. From microscopic plankton to massive blue whales, from the icy tundra to the fiery heart of volcanoes, Earth's living systems weave a story of endurance and beauty that exists nowhere else in the cosmos. At least, not that we've found. Life on Earth is the universe's grand experiment in possibility, a reminder that under the right conditions, the line between rock and consciousness can blur, and the cosmos can know itself through the eyes of living beings. Yet this boundless variety doesn't exist in isolation. It is shaped and sustained by the movements of the planet itself, by the oceans that regulate its climate and nourish its ecosystems. To truly understand life's diversity, we must follow the currents that drive Earth's vast marine engine, the ever-flowing pulse of the oceans, and currents that sustain the rhythm of our living world. The oceans are far more than vast stretches of water. They are the lifeblood of Earth's climate, the great engine that drives the planet's weather, shapes ecosystems, and sustains life on an unimaginable scale. Covering more than 70% of Earth's surface and containing over 97% of its water, the oceans are the primary regulators of global temperature and atmospheric circulation. Every wave that crashes against the shore and every deep current that flows beneath the surface is part of a massive, interconnected system, a planetary engine that keeps Earth's climate stable and habitable. At the heart of this system are the ocean currents, vast rivers within the sea that move heat, nutrients, and energy around the globe. These currents are not random. They are driven by a complex combination of forces, including wind patterns, Earth's rotation, salinity, and temperature differences. Together, they form a dynamic, self-regulating network known as the global ocean conveyor belt, or thermohaline circulation, from thermo for heat and haline for salt. This enormous system of water movement connects all 5 of Earth's oceans: the Pacific, Atlantic, Indian, Southern, and Arctic, into one continuous loop of motion that can take a single molecule of water up to 1,000 years to complete its journey around the planet. Warm surface currents begin near the equator, where the sun's energy heats the water, making it less dense and causing it to flow toward the poles. One of the most famous of these is the Gulf Stream, a powerful current that carries warm tropical water from the Caribbean across the North Atlantic. As this warm water travels north, it releases heat into the atmosphere, moderating temperatures in regions like Western Europe, which remain relatively mild even at high latitudes. Without the Gulf Stream, London and Paris might experience climates similar to those of northern Canada. When this water reaches the polar regions, it cools and becomes saltier due to sea ice formation. The increased density causes it to sink into the deep ocean, where it begins a slow journey back toward the equator. This sinking of cold, dense water, particularly in the North Atlantic and around Antarctica, drives the entire conveyor belt, pulling warm surface waters northward in a continuous cycle. The process is essential for balancing global heat distribution. Without it, the equatorial regions would grow unbearably hot, while the poles would plunge into deep freeze. Beyond temperature regulation, ocean currents profoundly influence weather patterns and climate stability. For example, the El Niño Southern Oscillation, ENSO, in the Pacific Ocean is a periodic fluctuation in water temperature that affects weather worldwide. During an El Niño event, warmer waters in the central and eastern Pacific shift rainfall patterns, bringing heavy floods to some regions and severe droughts to others. Its counterpart, La Niña, brings cooler ocean temperatures and often intensifies hurricanes and monsoon cycles. These oscillations demonstrate just how deeply oceanic conditions are intertwined with atmospheric behavior. A delicate partnership scientists refer to as ocean-atmosphere coupling. The oceans also store and absorb immense amounts of carbon dioxide from the atmosphere, acting as a giant carbon sink. Tiny marine organisms such as phytoplankton, microscopic plants floating near the surface, play a vital role in this process. Through photosynthesis, they absorb carbon dioxide and release oxygen, producing more than half of the oxygen we breathe. When these organisms die, some of their carbon sinks to the ocean floor, effectively trapping it in sediments for millennia. This biological pump helps regulate the planet's carbon balance and keeps Earth's climate in check. But the oceans do more than regulate heat and gases. They also distribute life itself. Currents carry nutrients from the deep sea up to the surface in a process called upwelling, fueling massive blooms of plankton that form the base of the marine food chain. These nutrient-rich waters sustain fish populations, seabirds, and whales, creating some of the most productive ecosystems on Earth. Regions such as the Peruvian coast or the Benguela Current off southern Africa are thriving examples of how upwelling zones feed both marine life and human communities that depend on fishing. The relationship between oceans and the atmosphere is a two-way street. The sun heats the ocean's surface, causing evaporation that adds moisture to the air, which in turn fuels cloud formation and precipitation. This exchange is the foundation of the water cycle, determining rainfall, droughts, and storms across continents. When warm ocean waters evaporate rapidly, they can spawn massive tropical cyclones, hurricanes and typhoons that carry enormous amounts of heat and energy from sea to land. In this way, the oceans act not only as climate moderators, but also as the architects of some of Earth's most powerful weather phenomena. Even subtle changes in ocean circulation can have dramatic impacts on global climate. Scientists studying ancient ice cores and sediments have found evidence that shifts in the thermohaline circulation have triggered past ice ages and abrupt warming events. Today, there is concern that climate change could disrupt these delicate systems. As polar ice melts and fresh water pours into the oceans, salinity levels drop, potentially weakening the sinking of cold water that drives the conveyor belt. A slowdown in these currents could lead to severe regional climate changes, altering rainfall patterns, reducing nutrient upwelling, and even cooling parts of Europe despite global warming. Yet for now, the oceans continue their tireless work, breathing, circulating, and nurturing the planet. They are the lungs and heart of Earth, absorbing excess heat, generating oxygen, and giving birth to weather. Every gust of wind, every raindrop, every gentle wave breaking on a beach is connected to the deep and constant motion of the seas. In their silent rhythm, ocean currents embody both power and harmony. They are ancient and enduring, the unseen architects of climate and life. Without them, Earth would be a planet of extremes, scorched at the equator, frozen at the poles, and devoid of the balance that makes life possible. But even as these immense blue forces maintain stability, their influence does not stop at the horizon. The same energy and heat that circulate through the oceans rise into the skies, shaping clouds, winds, and the shifting moods of the planet's atmosphere. From the stillness of a calm day to the fury of a hurricane, the next chapter in Earth's grand design unfolds above us, in the ever-changing realm of weather and climate. The Earth's weather is a constantly shifting symphony of heat, air, and moisture, an endless dance between ocean and sky, sunlight and shadow. It is the planet's most visible expression of energy in motion. Each gust of wind, each falling raindrop, every storm and sunset arises from the same fundamental process: the transfer of heat from the sun through our atmosphere. Yet while weather is the day-to-day rhythm of this energy exchange, climate is its long, steady melody, the pattern that emerges over centuries and shapes the living world in profound ways. At its heart, Earth's weather begins with the sun. The sun's rays strike the planet unevenly because of its curvature. The equator receives intense, direct sunlight, while the poles are bathed in weaker, angled rays. This unequal heating sets everything into motion. Warm air, being lighter, rises near the equator, creating areas of low pressure. Cooler, denser air from higher latitudes flows in to replace it. This constant exchange of warm and cool air drives wind, the invisible force that moves moisture and heat across the globe. As warm, moist air rises, it cools and condenses, forming clouds, vast floating fields of tiny water droplets or ice crystals. When enough of this moisture accumulates, gravity pulls it down as rain, snow, or hail, replenishing rivers, lakes, and soils below. These processes form the foundation of the water cycle, an unending exchange that connects ocean to atmosphere to land and back again. Without it, there would be no rainforests, no rivers, and no life as we know it. The movement of air around the planet is organized into vast, circulating belts known as atmospheric circulation cells. Near the equator, rising air creates the Intertropical Convergence Zone, ITCZ, a band of frequent storms and heavy rainfall that shifts with the seasons. This region is responsible for the lush rainforests of the tropics. As the air spreads poleward, it cools and sinks around 30 degrees latitude, forming dry zones and deserts such as the Sahara and Arabian deserts. Farther north and south, other circulation cells, the feral and polar cells, shape temperate and frigid climates. These great wind systems, including the trade winds, westerlies, and polar easterlies, steer storms, influence ocean currents, and determine the flow of weather across continents. The rotation of the Earth adds another layer of complexity. As the planet spins, moving air is deflected by the Coriolis effect, curving winds to the right in the northern hemisphere and to the left in the southern. This deflection gives rise to swirling storm systems and jet streams, high-altitude rivers of fast-moving air that can stretch for thousands of kilometers. Jet streams guide the paths of cyclones and anticyclones, determining where rain falls, where heat waves linger, and where cold fronts form. Moisture, too, is central to Earth's weather. The oceans, which cover most of the planet's surface, act as vast reservoirs of water vapor. As sunlight warms the sea, evaporation fills the air with moisture, fueling the formation of clouds and storms. When this energy is released through condensation, it drives some of the most powerful weather events on Earth: thunderstorms, hurricanes, and tornadoes. A single tropical cyclone can release more energy in a day than all the world's power plants combined, yet it also redistributes heat from the tropics toward the poles, helping balance the planet's temperature. Every region on Earth experiences weather differently, shaped by its latitude, geography, and proximity to oceans. Coastal areas enjoy moderate temperatures due to the sea's ability to absorb and release heat slowly, while inland deserts experience dramatic highs and lows within a single day. Mountains block moist air and create rain shadows, where one side is lush and the other arid. In polar regions, frigid air dominates year-round, while tropical zones pulse with thunderstorms and monsoons. These local variations combine into the greater, long-term patterns that we call climate. Where weather is temporary, changing within hours or days, climate represents the average of those conditions over decades, centuries, or even millennia. It encompasses the broader trends that define regions: tropical, temperate, polar, arid, or continental. For instance, a rainy afternoon in the Sahara doesn't change the fact that its climate is a desert one. Climate sets the stage, while weather plays the daily script. Earth's climate system is an intricate balance between the atmosphere, oceans, land, and biosphere, all linked by the flow of energy. The greenhouse effect is one of the most vital components of this system. Naturally occurring gases, water vapor, carbon dioxide, methane, and others, trap some of the sun's heat within the lower atmosphere, preventing it from escaping into space. Without this natural insulation, Earth's average temperature would plummet to around -18 degrees Celsius, 0 degrees Fahrenheit, rendering the planet frozen and lifeless. But because of it, the global average temperature hovers near 15 degrees Celsius, 59 degrees Fahrenheit, just right for liquid water and life. However, this delicate balance can be disrupted. Over geological timescales, volcanic eruptions, shifts in Earth's orbit, and changes in ocean circulation have caused natural climate fluctuations, ice ages, and warm periods that shaped the evolution of species. But in the modern era, human activities have become a powerful new force. The burning of fossil fuels, deforestation, and industrial emissions have increased greenhouse gases to levels unseen in millions of years, intensifying the greenhouse effect and driving global temperatures upward. This shift, known as climate change, is altering weather patterns worldwide, increasing the frequency of heat waves, droughts, floods, and storms. Despite these challenges, the study of weather and climate reminds us of Earth's incredible resilience and complexity. Meteorologists and climatologists today use satellites, computer models, and centuries of observation to understand and predict how our planet behaves. From tracking hurricanes to studying polar ice cores, their work reveals that weather and climate are not chaotic. They are interconnected systems responding to physical laws and human influence alike. Ultimately, both weather and climate shape the living world. They determine where rainforests thrive and where deserts spread, where humans can grow crops, and where animals migrate. They influence civilization itself, guiding agriculture, architecture, and culture across millennia. And yet, as varied as Earth's climates may be, life has found ways to adapt to nearly every one of them. From the scorching heat of deserts to the icy stillness of Antarctica, our planet shelters organisms that endure the extremes, a testament to evolution's unending creativity. As we move from the ever-changing skies to the harshest corners of the Earth, we discover the extraordinary resilience of life itself in the most extreme environments our planet has to offer. Earth, for all its beauty and balance, is also a planet of extremes, a world that pushes the limits of what life can endure. From the blistering deserts scorched by relentless sun to the frozen wastelands buried beneath ice, and from the crushing depths of the ocean to the thinnest air atop the highest mountains, Earth's environments test the very definition of survival. Yet astonishingly, life not only persists in these places, it thrives. Every extreme environment on our planet tells a story of resilience, adaptation, and the boundless inventiveness of evolution. Consider first the Atacama Desert in northern Chile, one of the driest places on Earth. Some weather stations in its core have recorded no rainfall for over 400 years, and the region's average annual precipitation is less than 1 millimeter, drier even than Mars's surface in some areas. The landscape is so barren and desolate that NASA has used it as a testing ground for Martian rovers and instruments designed to search for life on other planets. Here, the ground is crusted with salt, the air is thin and cold at night, and ultraviolet radiation from the sun beats down mercilessly. And yet, life endures, hidden in rocks and soil. Microorganisms, known as extremophiles, have adapted to extract moisture from the faint morning fogs and live on minerals in the salt. These hardy bacteria and fungi are reminders that life can flourish even in conditions where it seems impossible. A testament to the persistence of biology in the face of planetary hostility. On the opposite end of the spectrum lies Antarctica, the coldest, driest, and windiest continent on Earth. It holds 70% of the world's fresh water in the form of ice, and temperatures can plunge below -80 degrees Celsius, -112 degrees Fahrenheit, during the long, sunless winter. Its interior receives less precipitation than many deserts, technically making it a polar desert. Yet beneath its ice sheets and within its frigid waters, life has carved out astonishing niches. Tiny algae and bacteria bloom in the thin films of liquid water between ice crystals. Penguins, seals, and whales depend on the nutrient-rich Southern Ocean that surrounds the continent, which bursts with plankton and krill during the brief summer. Even in the subglacial lakes sealed under kilometers of ice, such as Lake Vostok, scientists have found microbial life that may have been isolated for millions of years, living in total darkness and extreme pressure. Antarctica reminds us that even in the harshest cold, warmth still flickers in the form of life's persistence. Then there is the Mariana Trench, the deepest known part of Earth's oceans, plunging nearly 11,000 meters, 36,000 feet, below the surface, deeper than Mount Everest is tall. Down there, sunlight never reaches, the temperature hovers just above freezing, and the pressure is over 1,000 times greater than at sea level. To the human body, such conditions would be instantly fatal. Yet, even here, in the abyssal darkness, life thrives. Strange, ghostly creatures, amphipods, snailfish, and bioluminescent bacteria drift through the blackness, illuminating the deep with faint, eerie glows. Microbes cling to hydrothermal vents and cold seeps, drawing energy not from sunlight, but from the chemical reactions of Earth's interior. This process, called chemosynthesis, allows life to exist completely independent of the sun. A discovery that forever changed our understanding of what it means to be habitable. These environments are not isolated curiosities. They are essential chapters in Earth's story. They show that life's boundaries are not defined by comfort, but by adaptation. In the blistering heat of Ethiopia's Dalol hydrothermal fields, where temperatures reach over 100 degrees Celsius, 212 degrees Fahrenheit, and pools bubble with acid as corrosive as battery fluid, microbes have been found that tolerate both the heat and acidity. In the Chernobyl exclusion zone, fungi have evolved to use radiation as an energy source. In the deep caves of Mexico, bacteria feast on sulfur and survive without oxygen. Even in the upper layers of the stratosphere, nearly 40 kilometers above Earth's surface, scientists have detected hardy microorganisms carried on dust and volcanic ash. Each of these environments is a laboratory of survival, a living experiment in how life bends, stretches, and transforms to meet the demands of its surroundings. These extremophiles have not just adapted to endure, they have turned adversity into opportunity. By studying them, scientists gain insight into the possible forms life could take elsewhere in the universe. The bacteria that live in the Atacama's salt rocks, for example, may resemble potential Martian microbes. The creatures of the deep sea vents could parallel the life that might exist on icy moons like Europa or Enceladus, where subsurface oceans churn beneath layers of ice. Earth's extremes also challenge human endurance. Explorers who have climbed Mount Everest, where the air contains only 1/3 of the oxygen at sea level, have experienced firsthand how delicate the balance of life is. At the other end, deep-sea submersibles have descended into the Mariana Trench, where human-made machines must withstand pressures equivalent to the weight of 50 jumbo jets. In space, astronauts face a new kind of extreme: vacuum, radiation, and isolation. Yet they are guided by lessons learned from the harshest environments of our home planet. Despite their hostility, these extreme places play vital roles in the Earth's systems. The polar ice caps regulate the planet's temperature by reflecting sunlight, acting as Earth's thermostat. Deep ocean trenches recycle the crust through subduction, renewing the surface of the planet. Deserts like the Atacama and the Sahara produce dust that fertilizes distant rainforests across oceans. Even volcanic landscapes, with their toxic gases and searing heat, release minerals that enrich the soil and sustain life when the land cools. In this way, even the most inhospitable places contribute to the balance that keeps Earth alive. It's humbling to realize that our planet, though teeming with life, has always bordered on the edge of the extreme. Earth is both nurturing and unforgiving, a world where ice and fire coexist, where pressure, temperature, and radiation create both barriers and opportunities for life. Its extremes define its beauty. Yet, before life could conquer these harsh frontiers, Earth itself had to undergo one of the most profound transformations in its history, a revolution that changed the very air we breathe. Billions of years ago, a subtle shift in chemistry gave rise to oxygen and, with it, the possibility for complex life to emerge. This event, known as the Oxygen Revolution, marks one of the greatest turning points in our planet's story, the moment when the world truly came alive. Roughly 2.5 to 2.7 billion years ago, Earth was a radically different world, one most of us would not even recognize as our home. The skies were tinted orange with methane haze, the oceans were greenish and iron-rich, and the air was thick with gases toxic to the forms of life we know today. Oxygen, the element we now depend on for every breath, was almost entirely absent. The surface of the planet was dominated by single-celled organisms living in an atmosphere of carbon dioxide, methane, ammonia, and nitrogen. And yet, from this alien world, a quiet revolution began, one that would transform the planet's chemistry, sculpt the atmosphere, and eventually make possible the emergence of animals, plants, and, ultimately, humanity itself. This epoch-defining transformation is known as the Oxygen Revolution, or more formally, the Great Oxidation Event, GOE. The key players in this transformation were humble yet extraordinary microorganisms known as cyanobacteria, tiny architects of Earth's destiny. They were among the first life forms to master the process of photosynthesis, the ability to use sunlight, carbon dioxide, and water to produce energy. But their version of photosynthesis was unique. It was oxygenic photosynthesis, meaning that it released oxygen as a byproduct. Through this elegant chemistry, 6CO, 2 plus 6, H2O plus sunlight, C6H12, O6 plus 6, O2. Cyanobacteria turned sunlight into fuel and began to fill the oceans with oxygen molecules for the first time in planetary history. At first, this change went unnoticed. The oxygen produced by these microorganisms didn't accumulate in the air right away. Instead, it reacted with the iron dissolved in the early oceans. The iron oxidized, or rusted, and sank to the seafloor, forming massive deposits of banded iron formations that we still mine today. These ancient rock layers, striped with alternating bands of red, oxidized iron, and grey, iron-rich minerals, are the geological fingerprints of life's first great transformation of the planet. Once the ocean's iron was consumed, oxygen began to build up in the atmosphere itself. Around 2.4 billion years ago, this accumulation reached a tipping point. The Great Oxidation Event had begun. For the first time, Earth's atmosphere contained significant levels of free oxygen, an event so profound it fundamentally altered the course of the planet's evolution. What followed was both a catastrophe and a miracle. For the early anaerobic life forms, those that thrived in the absence of oxygen, this new gas was a deadly poison. Oxygen, highly reactive, damaged their cellular machinery. Countless microbial species perished in what was, effectively, the first mass extinction in Earth's history. Yet, while it spelled doom for many, it also opened doors to entirely new possibilities. Life had been gifted a new and powerful form of energy production: aerobic respiration. Unlike anaerobic processes, which yield only a small amount of energy from food, aerobic respiration is far more efficient. It allows organisms to extract nearly 18 times more energy per molecule of glucose than before. This abundance of energy paved the way for the evolution of larger, more complex, and more active life forms. Oxygen didn't just change the chemistry of Earth, it rewired the potential of biology itself. The Great Oxidation Event also transformed Earth's geology and climate. As oxygen reacted with methane, a potent greenhouse gas, in the atmosphere, it reduced the planet's overall greenhouse effect. This dramatic shift likely triggered one of the most severe ice ages in Earth's history, known as the Huronian glaciation, when vast ice sheets spread across the globe, possibly reaching even the equator. It was as though the planet was temporarily plunged into a frozen stillness before life adapted to the new oxygen-rich reality. But from that freeze came renewal. The buildup of oxygen set in motion a chain of events that eventually led to the formation of the ozone layer, a thin but critical shield of O3 molecules high in the atmosphere. The ozone layer absorbed the sun's most harmful ultraviolet radiation, allowing life to safely expand from the oceans onto land hundreds of millions of years later. Before this, the planet's surface was a deadly place, bombarded by UV radiation that could shred DNA. With ozone in place, life was free to explore new realms. Over time, oxygen levels continued to fluctuate. For nearly 1 billion years after the Great Oxidation Event, Earth's atmosphere remained only partially oxygenated. Then, around 600 million years ago, another surge in oxygen, known as the Neoproterozoic Oxygenation Event, helped spark one of the most dramatic bursts of biological innovation in history, the Cambrian explosion. In this relatively short geological period, about 541 million years ago, life diversified explosively, giving rise to most of the major animal groups that still exist today. This leap into complexity, from single cells to multicellular organisms with specialized tissues, skeletons, and nervous systems, would not have been possible without oxygen. It provided the metabolic energy needed to sustain larger bodies, active movement, and complex ecological interactions. In essence, oxygen became the fuel of evolution's creativity, enabling the emergence of fish, plants, insects, mammals, and, eventually, humans. The oxygen revolution also forever altered the appearance of our planet. The skies turned from orange to blue as methane levels dropped and oxygen replaced it. The oceans, once green and murky with dissolved iron, became clear and blue as iron precipitated out. The air grew breathable and the seas became oxygenated, allowing new ecosystems to form. What had once been an alien world became the vibrant, life-filled Earth we recognize today. Even now, the legacy of cyanobacteria endures. They still exist. In fact, they are everywhere. They float in the oceans as part of phytoplankton, blanket rocks and soil in thin mats, and even inhabit extreme environments like hot springs and deserts. They remain one of the planet's most vital life forms, producing an estimated 20 to 30% of the oxygen in the atmosphere today. Every breath we take, every flame that burns, every heartbeat that depends on oxygen owes a silent debt to these ancient architects of life. The oxygen revolution also offers humbling insight into Earth's fragility and resilience. It shows that life doesn't merely adapt to its environment, it transforms it. The atmosphere we breathe is not a passive feature of the planet, but a biological creation, sculpted by living organisms over eons. It's a reminder that the biosphere and the planet's chemistry are intertwined in a feedback loop, each shaping the other in ways both subtle and profound. And as life evolved and diversified, another force began to emerge, one that would eventually alter Earth's balance again. Billions of years after cyanobacteria filled the sky with oxygen, a new species appeared that learned to harness the planet's resources at unprecedented speed: humans. Just as ancient microbes changed the air, humans have begun to change the atmosphere once more, but in ways that threaten to undo the balance nature achieved. The next chapter in Earth's story is both cautionary and hopeful. The tale of human impact, the age where one species holds the power to harm or heal the only world known to harbor life. In the grand timeline of Earth's 4.54 billion year history, humanity's presence is but a fleeting moment, and yet, in that brief instant, no species has ever transformed the planet so profoundly. From the moment early humans learned to harness fire to the industrial age of machines, from the agricultural revolution to the digital era, our species has left an unmistakable mark on every corner of the world. We have become a geological force, reshaping landscapes, altering the atmosphere, and even influencing the chemistry of the oceans. Scientists now refer to this period as the Anthropocene, an age defined by human impact. Our story is one of both creation and consequence. Humanity's ingenuity has allowed us to thrive, but it has also pushed Earth's systems to their limits. Through deforestation, pollution, and climate change, we've altered the natural balance that sustains life, the same balance that took billions of years to achieve. Deforestation stands as one of our most visible imprints. Vast forests, once spanning continents, have been cleared to make way for agriculture, urbanization, and industry. Over 10 million hectares of forest are lost every year, an area roughly the size of Portugal. The great tropical rainforests, from the Amazon to the Congo Basin and Southeast Asia, are particularly affected. These forests are not just collections of trees, they are living systems, producing oxygen, storing carbon, regulating rainfall, and providing homes for countless species. When they fall, biodiversity vanishes, carbon is released into the air, and the very lungs of the planet begin to struggle for breath. Pollution adds another layer to this crisis. From the depths of the ocean to the peaks of the Himalayas, no ecosystem remains untouched by human waste. Plastic, once hailed as a miracle material, now litters every corner of the planet, with an estimated 8 million tons entering the oceans each year. Microplastics have been found in fish, snow, and even the air we breathe. Meanwhile, industrial emissions and agricultural runoff poison rivers and soil, threatening both wildlife and human health. The air in many major cities is thick with smog, and the oceans are turning more acidic as they absorb excess carbon dioxide, a phenomenon that weakens coral reefs, dissolves shells, and disrupts marine food chains. But it is climate change, driven largely by the burning of fossil fuels, that represents humanity's greatest challenge and perhaps its greatest test of responsibility. Since the dawn of the Industrial Revolution, atmospheric carbon dioxide levels have risen from about 280 parts per million ppm to over 420 ppm, the highest concentration in more than 3 million years. This surge traps more heat in the atmosphere, raising global temperatures, melting polar ice, and intensifying weather patterns. The consequences are already evident: longer droughts, fiercer wildfires, more destructive hurricanes, and rising sea levels that threaten coastal communities. The Arctic is warming 4 times faster than the rest of the planet, and ancient glaciers, once thought eternal, are vanishing before our eyes. Yet even as these changes accelerate, humanity's story is not one solely of destruction. It is also one of awareness, innovation, and renewal. For every harm we've caused, there are countless efforts being made to restore balance. Around the world, reforestation projects are taking root, from the Great Green Wall Initiative in Africa, designed to halt desertification, to large-scale tree planting campaigns in Asia, Europe, and the Americas. Scientists and conservationists are working to protect endangered species and restore damaged ecosystems, recognizing that every organism plays a part in the planet's web of life. Renewable energy is emerging as a beacon of hope. Solar, wind, geothermal, and hydroelectric technologies are expanding rapidly, offering alternatives to coal, oil, and gas. Cities are redesigning themselves to be greener and more sustainable, with innovations like electric transportation, vertical gardens, and zero-waste systems. Around the globe, individuals are adopting more conscious lifestyles, reducing consumption, reusing resources, and rethinking what progress means in an interconnected world. The fight against climate change has also united nations in an unprecedented way. Agreements such as the Paris Climate Accord have brought countries together under a shared commitment to limit global warming and transition to sustainable economies. While progress is uneven and often slow, the very existence of these collaborations shows that humanity is capable of collective action, of learning from its past and striving toward a wiser future. At the same time, new technologies are helping us understand and protect our planet better than ever before. Satellites track deforestation and pollution in real time. Artificial intelligence models predict climate patterns and optimize energy use. Scientists are studying ways to capture carbon directly from the atmosphere and restore degraded lands. Even ancient knowledge, the wisdom of indigenous communities who have lived in harmony with nature for millennia, is being rediscovered and respected as a guide for sustainable coexistence. There is also a growing recognition that healing the planet begins with empathy, not just for the natural world, but for one another. Environmental degradation often hits the most vulnerable communities hardest, from island nations facing rising seas to farmers struggling with droughts. Protecting the planet, therefore, is also an act of protecting humanity itself. The human impact on Earth is vast, but it is not irreversible. The same intelligence that enabled us to reshape the planet also gives us the power to repair it. Each generation now carries both the burden and the privilege of choice, to continue exploiting or to begin restoring. The outcome will determine not only the state of the environment, but the legacy we leave for every form of life that shares this fragile world with us. Despite our flaws, humanity is capable of remarkable resilience and creativity. We have looked inward and seen the damage we've done, but we've also looked outward. From the surface of the moon, from space stations orbiting above, and seen Earth for what it truly is, a small, glowing oasis in a vast, dark universe. That image has inspired countless people to care more deeply, to act more wisely, and to protect what we once took for granted. And it is within this recognition that Earth is not just a resource, but a living home. That hope resides. From here, we turn from the story of human influence to the story of nature's own majesty, the breathtaking marvels carved not by hands, but by time, wind, and water, the planet's natural wonders, testaments to both its power and its fragility. Across the vastness of our planet, there exist places so awe-inspiring, so breathtakingly magnificent, that they seem almost otherworldly. These are Earth's natural wonders, living sculptures shaped not by human hands, but by the timeless interplay of wind, water, fire, and tectonic force. They stand as both masterpieces and memoirs, chronicling the planet's evolution across eons. From the depths of oceanic coral kingdoms to the towering peaks that pierce the sky, these wonders remind us of Earth's power to create beauty through pressure, time, and chaos, and of our small but privileged place within it. One of the most iconic of these marvels is the Grand Canyon in the southwestern United States, a colossal chasm stretching for more than 440 kilometers, 277 miles, and plunging over 1.6 kilometers, a mile deep. To stand on its rim is to gaze directly into the planet's past. Each layer of its multicolored walls represents a chapter in geological history, some dating back nearly 2 billion years. Formed primarily by the erosive power of the Colorado River, the canyon is the result of relentless persistence, the river slicing through rock over millions of years, aided by wind, rain, and time. The rock strata tell stories of ancient seas, shifting deserts, and long-vanished ecosystems. The Grand Canyon is not simply a gorge, it's a timeline carved in stone, revealing how patient natural forces can transform solid rock into art. If the Grand Canyon is a monument to erosion, then the Great Barrier Reef is a celebration of life's creative power. Stretching over 2,300 kilometers, 1,400 miles, along Australia's northeastern coast, it is the largest living structure on Earth, so vast it can be seen from space. Composed of billions of tiny coral polyps, the reef is a thriving city of color and motion. Every coral, fish, sponge, and crustacean plays a part in its intricate web of life. Over thousands of years, corals built this undersea cathedral by secreting calcium carbonate skeletons, layer upon layer, forming reefs, cays, and lagoons that host more than 1,500 species of fish and 400 types of coral. But the Great Barrier Reef is also fragile, vulnerable to rising ocean temperatures, acidification, and pollution. Its beauty, therefore, is a poignant symbol of both nature's abundance and its delicate dependence on balance. Far above the seas, the world's highest mountain rises like a silent sentinel, Mount Everest. Standing 8,848 meters, 29,032 feet, above sea level, it is the crown of the Himalayas, a range formed when the Indian plate collided with the Eurasian plate around 50 million years ago. That colossal impact pushed seabeds skyward, creating some of the most dramatic peaks on the planet, Everest among them. Even today, the mountain continues to rise a few millimeters each year as the tectonic plates still grind together. On its slopes, climbers tread upon rocks that were once part of the ancient ocean floor, rich with marine fossils, proof that the highest point on Earth was once underwater. Everest's harsh winds, thin air, and freezing temperatures make it a place where few can survive. Yet it stands as a symbol of human determination and the ceaseless power of geology. Other natural wonders tell stories just as profound. The Aurora Borealis and Aurora Australis, the shimmering curtains of light near Earth's poles, are the result of charged solar particles colliding with gases in our upper atmosphere. These ethereal displays, greens, purples, and reds dancing across the sky, are living reminders of the planet's magnetic shield and its fragile connection to the sun. The Sahara Desert, the largest hot desert in the world, is a sea of sand sculpted by the wind, its dunes rising like waves frozen in time. Once lush and green thousands of years ago, it transformed through shifts in Earth's orbit and climate cycles, an example of the planet's ability to reinvent itself. Beneath the surface, The marble caves of Patagonia in Chile reveal another face of beauty. Vast caverns carved by glacial meltwater over thousands of years. Their walls swirl with patterns of blue and white, reflections of the surrounding lake and sky. Similarly, Iguachu Falls, on the border of Brazil and Argentina, thunder with the energy of 275 individual cascades pouring over basalt cliffs that once flowed with lava. Standing before them, one can feel the raw power of water reshaping stone, one drop at a time. In North America, Yellowstone National Park offers a glimpse into Earth's fiery heart. Beneath its geysers and hot springs lies a massive volcanic system, a reminder that our planet's core remains alive and restless. The vibrant colors of the grand prismatic spring, from deep blue to fiery orange, are created by heat-loving microorganisms that thrive in the hot, mineral-rich waters. Each hue represents a different species adapted to a precise temperature range, showcasing how even extremity can nurture life. Then there is Mount Kilimanjaro in Africa, a solitary giant rising from the plains of Tanzania. Its snow-capped summit, though only a few degrees south of the equator, stands as a stark contrast to the surrounding savanna. Formed by volcanic activity, Kilimanjaro's ice fields are retreating year by year, a silent witness to a changing climate. The same is true of the Galapagos Islands, where volcanic origins and isolation have created an evolutionary laboratory, a place that inspired Charles Darwin to uncover the principles of natural selection. These wonders, though separated by geography and form, share a common thread. They are products of Earth's restless energy. Plate tectonics lifts mountains and creates ocean trenches. Rivers and glaciers carve valleys. Volcanoes build islands. Winds sculpt deserts. Life itself shapes the land through coral growth and soil formation. Even time, that invisible sculptor, plays a crucial role, wearing down what once rose high and raising what once lay hidden. But these marvels are not eternal. Just as they were born from change, they are also vulnerable to it. The Grand Canyon continues to erode, inch by inch. The Great Barrier Reef faces bleaching from warming seas. Everest's glaciers are melting, and the auroras flicker under the influence of solar storms. The same natural processes that gave rise to these wonders, erosion, movement, heat, also guarantee their transformation. They are, in a sense, living phenomena, always in flux. Yet, it is precisely this impermanence that gives them meaning. To witness Earth's natural wonders is to glimpse deep time, to see the slow, patient artistry of the planet revealed in a single moment of human awareness. They remind us that the ground beneath our feet is alive, that beauty can emerge from pressure and violence, and that our planet, though ever-changing, remains infinitely capable of renewal. From the canyon's carved depths to the reef's living brilliance, from the desert's silence to the mountain's roar, Earth's natural wonders are not just sights to behold, they are stories in motion, each one a testament to the forces that shape this world. And as we look back from above, from the perspective of those who have seen our planet from space, these wonders merge into a single, breathtaking vision. A fragile blue world adrift in the dark, vibrant and alive beyond measure. That vision brings us to the next part of Earth's story, how it appears when seen from the edge of the void. A glowing, delicate sphere that has stirred the hearts of astronauts and changed the way humanity understands its place in the universe. This is the story of Earth from space, a perspective that unites awe, humility, and a renewed sense of guardianship for the only home we have. From the silent expanse of space, where the stars burn cold and eternal, Earth appears as something almost impossibly delicate, a glowing sphere of blue and white, suspended in darkness. Astronauts who have seen our planet from this vantage point often struggle to describe the experience in words. They speak of beauty beyond imagination, of awe so profound it reshapes their understanding of existence. From a few hundred kilometers above, the details of nations and borders disappear, and what remains is unity, a single living world, fragile yet fiercely alive. This transformative realization has come to be known as the overview effect, a shift in consciousness that forever changes how one perceives Earth and humanity's place upon it. When Apollo 8 astronauts orbited the Moon in 1968, they became the first humans to see Earth rising over another world's horizon. As astronaut William Anders captured the iconic photograph known as Earthrise, he uttered words that echoed through history. "We came all this way to explore the Moon, and the most important thing is that we discovered the Earth." That image, a small, radiant sphere hovering above the grey, lifeless surface of the Moon, awakened something collective within humanity. It revealed the truth of our shared home, finite, borderless, and astonishingly beautiful. Seen from space, Earth is a canvas of contrasts. Swirling white clouds trace the patterns of the atmosphere. Vast blue oceans shimmer under sunlight. Golden deserts stretch endlessly, and green continents breathe beneath drifting shadows. The thin, faint line of the atmosphere, just a few dozen kilometers thick, encircles the globe like a fragile veil, protecting everything we know from the cold void. Astronauts describe it as almost translucent, a glowing band of pale blue light separating life from lifelessness. To see it from space is to understand, at a visceral level, just how delicate the balance of life truly is. Many who have looked back upon Earth from orbit or beyond have described an overwhelming sense of interconnectedness. They see no countries, no divisions, only one ecosystem, one climate, one people sharing a single, finite biosphere. The realization is humbling. As Apollo 14 astronaut Edgar Mitchell said, "You develop an instant global consciousness, a people orientation, an intense dissatisfaction with the state of the world, and a compulsion to do something about it." This, in essence, is the overview effect, the recognition that Earth is not a collection of separate nations, but a single organism, alive, interdependent, and precious. From low Earth orbit aboard the International Space Station, astronauts witness the world in constant motion. They see sunrises every 90 minutes, watch lightning storms flash across continents, and observe ribbons of green and purple aurora swirling near the poles. The sight of hurricanes spiraling across the oceans or wildfires glowing red through the night sky is both beautiful and sobering, a reminder of nature's power and of humanity's impact upon it. Yet from that distant perspective, even the most violent storms seem fleeting, and Earth's resilience shines through. The view of Earth from space has changed not only those who have experienced it firsthand, but also those who have seen it through their eyes and photographs. The blue marble image, taken by the Apollo 17 crew in 1972, became one of the most reproduced photographs in history. It showed Earth as a perfect sphere, bathed in sunlight, with Africa and the Middle East in clear view. For the first time, humanity saw its home whole and unbroken. That image fueled environmental awareness movements and inspired the creation of organizations dedicated to protecting the planet. It reminded us that we all live on the same island in the cosmic ocean. Later missions, from the Voyager, one spacecraft's pale blue dot image taken from 6 billion kilometers away, to modern satellite imagery that reveals Earth's dynamic systems in real time, have deepened this sense of perspective. When Carl Sagan described that distant dot as a mote of dust suspended in a sunbeam, he captured the essence of humility that space exploration brings. From such distance, all human achievements, conflicts, and histories compress into a single pixel. And yet, that pixel contains everything we love, everything we've ever known. The overview effect also carries a moral and spiritual dimension. Many astronauts return from space with a renewed sense of responsibility toward the planet. They speak of Earth as a living being, a sanctuary that must be protected. Some describe the experience as transcendent, a realization that everything on this planet is interconnected, and that harm to one part reverberates through the whole. This shift in consciousness, though sparked by a select few, has rippled outward to millions who have been inspired by their words, their images, and their awe. In this sense, space exploration has given humanity a mirror. By stepping beyond our home, we have come to understand it better. The thin blue line of the atmosphere reminds us that our survival depends on its preservation. The dark void surrounding Earth reminds us how rare and precious life is. And the glowing unity of continents and seas reminds us that our differences are small compared to what binds us together. The fragility seen from orbit is real. Earth's ecosystems are delicate, its resources finite, its stability dependent on balance. But from that same vantage point, there is also hope. The very sight of Earth from space proves that this small planet, adrift in the vastness of the cosmos, has achieved something miraculous. It sustains life. Against impossible odds, it thrives. And so, as astronauts return home and share their stories, their voices echo a single, powerful message. We are one species on one planet with one shared future. The overview effect is not just about awe. It is about responsibility, empathy, and connection. It is about realizing that protecting Earth is not a choice but a duty, not just for ourselves, but for the generations yet to come. As we turn from the view of our glowing world in the darkness of space, we come to the final realization in Earth's story, that this fragile, vibrant planet, so perfectly balanced and alive, is both our birthplace and our only home. And protecting it is not only an act of survival, but an act of love. As we reach the end of this journey through time, space, and wonder, one truth stands out above all others. Earth is irreplaceable. Among the billions of stars and uncountable planets scattered across the vast universe, there is, as far as we know, only one world like ours. One planet where oceans sparkle under sunlight, where forests breathe, where clouds dance across blue skies, and where life in all its astonishing forms thrives in delicate harmony. This is our home, not just for humanity, but for every creature, every tree, every drop of water and grain of soil that makes up the living fabric of the biosphere. Earth is unique, fragile, and astonishingly alive. From its fiery birth 4.54 billion years ago to the lush, vibrant world we inhabit today, Earth has been a story of balance. A balance between fire and ice, chaos and calm, destruction and renewal. It has endured collisions, extinctions, and cataclysms, yet through it all, life has persisted. Every mountain and canyon, every coral reef and forest, every whisper of wind and ripple of tide tells a story written by time itself, a story that we are now part of, and increasingly, the authors of. But for all its resilience, Earth is not invincible. The thin veil of atmosphere that protects us could easily be disrupted. The oceans that nourish us could turn against us if pushed too far. The stability that has nurtured life for billions of years depends on our ability to live in harmony, not in domination. We have reached a pivotal moment in that story, one where our choices will determine whether this planet remains a paradise of diversity and wonder, or whether it becomes a shadow of what it once was. Protecting Earth begins with curiosity. The same curiosity that drives explorers to cross oceans, scientists to study the stars, and children to dig their hands into the soil. Curiosity reminds us to look closer, to learn, to understand the intricate systems that make this world work. Because only when we understand something can we truly care for it. Every discovery, from the microorganisms that clean our oceans to the trees that breathe life into our air, deepens our connection to the planet and reminds us that everything here is interwoven. Next comes respect. Respect for the natural world and its rhythms. The forests do not need us, but we need them. The rivers do not ask for our gratitude, yet they sustain us. The earth gives generously, but it also demands balance. We must remember that progress and preservation are not opposites, they are partners. By respecting the limits of nature, we ensure that the future remains livable, not only for us, but for every generation that follows. And finally, action, the most powerful expression of gratitude and responsibility we can offer. Action doesn't always mean grand gestures. It begins with small, mindful choices: planting a tree, reducing waste, conserving energy, speaking up for the voiceless forests, oceans, and creatures that share our home. Each choice ripples outward, part of a collective movement to heal what has been harmed. Across the globe, millions of people are already acting, restoring habitats, protecting endangered species, reimagining cities, and creating sustainable solutions. These actions are seeds of hope, proof that it is not too late to make a difference. For when we protect Earth, we are not just saving landscapes or species, we are preserving the only known sanctuary for life in the universe. We are safeguarding the cradle of human civilization, the foundation of every dream, every art, every song ever sung. We are protecting the one world where love, consciousness, and creativity exist, where life looks up at the stars and dares to ask, "Are we alone?" Astronauts who have looked down on our planet from the vastness of space often say that Earth has no borders, no lines dividing people, only the soft glow of a shared home. That perspective, the overview effect, reminds us of something we too often forget. We are one species, bound by the same atmosphere, nourished by the same water, dependent on the same fragile systems. When we harm the Earth, we harm ourselves. When we nurture it, we nurture the future. So let us carry that vision with us, the image of a small, blue world shining in the darkness, and let it ignite in us a sense of wonder and responsibility. Let it remind us that every life, no matter how small, has a place and purpose here. Let it inspire us to explore, to protect, and to live gently on the land that sustains us. The story of Earth is still being written. Its chapters stretch into the unknown, and though we may not know how it ends, we have the power to shape the next lines. Whether this planet continues to flourish depends on what we choose today, whether we act with wisdom and reverence, or with indifference and greed. In the end, the message is simple yet profound. There is no planet B. This is our only home, our only chance, our shared miracle in the vast, silent universe. Let us honor it. Let us protect it. Let us keep the blue planet glowing, not just for ourselves, but for all who have come before and all who are yet to come. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.